You probably saw I posted a little bit from section 3.8. I'm not going to require much from you from that section, but I thought it was worth going over because of what we talked about on the written homework. That was a section that I had been debating whether to go over or not. So I decided I would go ahead and do it because of that. But that was essentially the last section on applications of derivatives that we are going to cover. So let me think. Are there any announcements I need to make? Let's see. I believe that I need to make a scheduling announcement. I think. Oh, nope, not yet. Yes, I do need to make a scheduling announcement. Do I? No, I don't. Take it back. I think that's it. Okay. So we can just carry on with this. Good morning. We are going to do section 3.9 today, which is on a subject called antiderivatives. So let's do that. Up till this point in our course, we have talked about a subject known as differential calculus, and that was as follows. Differential calculus. It was where we started with some function. Call that function y equals f of x. And using that function, we developed this list of rules and a process called differentiation. To find other related functions that we called derivatives. And those came in the form dy dx is equal to f prime of x, or we found higher order derivatives, d squared y dx squared is equal to f prime prime of x, etc. We were able to find higher order derivatives as well. In the second portion of this course, which is also a large portion of, or a significant portion at least, of Calc 2, if you were to take that, we're going to go backwards. So we're going to, for the remainder of this course at least, begin with a derivative and say, well, how do I go backwards and find the original function that was differentiated? And also, what are the applications of that process of starting with this function and working backwards and finding the original function? Okay, so that's just a bit of an introduction, and I'm going to do a lot of this by example. Okay, so let's see. Previously, when we introduced the derivative, we kind of talked about what it was, and then we introduced a list of rules that helped us to find the derivative. So maybe let's see if we can develop some rules for finding the antiderivatives, which is the backwards of differentiation. And let's start with this. Let's suppose I have the function f of x is equal to, or f prime, excuse me, is equal to 2x. So suppose that I've been given a function, I've differentiated it, and I've come to this derivative. You probably recognize that derivative. So you might think about, well, what was the original function that was differentiated? It was f of x is equal to x squared. F of x is equal to x squared. So if I were to differentiate f of x, I would get 2x. Okay? And you know that from what you've done with differentiation so far. But we might make an observation. Are there other functions that, when they are differentiated, give us the derivative 2x? For example, if the function g of x, say, is equal to maybe x squared plus 10, then I know that g prime is equal to 2x. If I'm given the function h of x is equal to, say, x squared minus 25, then the derivative h prime of x is equal to 2x as well. On the other hand, if I'm given something like maybe k of x is equal to, say, maybe x squared minus x, its derivative, k prime of x, is equal to, it's equal to the derivative of x squared, which is 2x, minus the derivative of x, which is 1, which is a little bit different. So I can look at this and I can say, well, these three functions, f, g, and h, all have the same derivative. So f prime of x is equal to g prime of x is equal to h prime of x. But k prime is slightly different. And that might give us an idea of kind of a pattern of what types of functions will give us the same derivative. So let's see this pattern here. I could write f of x as, say, the basic function is x squared, and then I could write it as maybe x squared plus 0. G of x is that same basic function x squared, and then 10 is added to it. H of x is that basic function x squared, and then I could write it as plus negative 25 maybe. All of those have the same derivative, but the original function has the addition of a constant term. And the reason for that is because the derivative of a constant is 0. So we have this addition of a constant. Addition of a constant. So it appears that if I am given the function f of x is equal to 2x, I need to modify the answer that I gave up here slightly. So let's see here. Let's modify what we set up there. That if f prime of x is equal to 2x, then I might say that f of x, the function that was differentiated, I know from my work here that all of these functions have that x squared term, but then there might be some constant c added to that function, where I don't necessarily know what this constant is. I'll just call it an arbitrary constant. But I do know that the function that this derivative came from had this specific form. Questions on that? Okay. This function I might call the antiderivative of 2x. Just like we have a specific notation for derivatives, we probably should, before we move on to specific rules for them, talk about the notation for antiderivatives as well. So let's do that. Talk about some notation. We will call capital F of x. This is not the notation I used previously, but for the definition your book gives, we're going to use capital F of x. We will call capital F of x the antiderivative of some function small f of x if I take the derivative of capital F of x and it happens to be equal to little f of x. So for what we did above, we used f prime of x and f of x. The f prime that we used previously would be the little f of x function below, and the f of x that we used would be capital F of x. And we're doing it this way because if you are asked to find an antiderivative, you are very often not given that function in this derivative notation. You're usually given it as a function in and of itself, and you're asked to backtrack and figure out, well, what was the function that it came from? But we have to just kind of understand that the function that we're given is a derivative, and we have to find its roots. Okay? If I am asked, and if I want to notate that my goal is to find this antiderivative, then I'm going to use the following notation. I'm going to use this elongated S symbol, and we'll talk later on about why we use that symbol. And then I'm going to put the function f of x that I'm interested in finding the antiderivative of. And then just like I have to notate my variable in differentiation, I'm going to notate it by the term dx, which is called a differential. So we'll call this the integral sign. The integral sign. And anytime it's sitting there in front of the function, just like a ddx term tells you to differentiate, this integral sign tells you, hey, this part is a derivative. I want you to work backwards and find its antiderivative. This part we would call the integrand. The integrand. And even though it's not notated with the prime notation, as mentioned, you can think of that part as a derivative. You can think of as a derivative that we want to find the antiderivative for. This part is called a differential. There we go. It is 8:15 in the morning. A differential, and it notates the variable of integration. So it notates the variable that we are dealing with. Variable of integration. So if I'm given that symbol, I know that this tells me that I want to find the antiderivative. That antiderivative, I can use capital F of x to notate, and just like we mentioned before, that capital F of x, if I'm given this notation, will have a arbitrary constant c added to it. So this is an arbitrary constant. And by arbitrary, I mean we just don't know what that constant is. This is also called the constant of integration. Constant of integration. And we call it the constant of integration because this whole term here is, it's a portion of a larger process that we would call integration. Anti-differentiation is a portion of this. So we call this whole thing the indefinite integral. The indefinite integral with respect to, or of f, excuse me, of the function f with respect to x. So this term here indicates that I want to find this term. So this term represents something called an integral. And this term, since those two are equal, represents the same thing. The indefinite part basically means I don't know what this constant c is. So I know that I can find the basic form, this part, but it is off by some unknown constant term that might be added or subtracted. Any questions so far about that? I know this is just notation, but. Okay. So now that I have a little bit of notation to work with, let's develop some rules by which we can find that indefinite integral or that antiderivative. Let's see. I will, just to clarify things slightly with the notation, if we above let f of x equal 2x, then by the rules I'm going to develop, we can say that the antiderivative, notated by that symbol, of 2x dx, or with respect to x, is equal to x squared plus c. Or this is my little f of x function, my integrand. This is my big f of x function. This is my antiderivative. This is the antiderivative. Also sometimes called the primitive. You might see that term on occasion. Which was fairly simple to figure out with that function. Now, let's see if we can figure out how to do that with other types of functions. I think I've said that about 3 times now, but let's actually do it. And I am going to lean very heavily on what you know about derivatives here, because that's where all of our rules for anti-differentiation come from. And I'm going to do it like this. Let's make a chart. Let's say this is the rule of anti-differentiation. Differentiation. And then on the right, I'm going to do an example leaning on differentiation. Okay, so as an example, let's start with this. Let's say, let's see, if I'm given the function y is equal to 2x and I want to find the derivative of that function, then I know how to do that by my previous rules. dy dx is equal to the constant 2. So if I want to go backwards and say, well, let me start with a constant 2 and let me anti-differentiate and get back to this original function, it appears that I just have to multiply that constant by x to get back to it. So I could use that as a rule. If I'm wanting to find the antiderivative of some constant k with respect to x, that antiderivative, or indefinite integral is another way to say it, is equal to k times the variable x, and then I have to add that constant c on the end. So that's one rule that I could develop. Questions on that? Okay, let's do a second one. Let's say if I'm given the function y is equal to maybe 1/3 x cubed, and I want to find the derivative of that, I can do that using my rules of differentiation. dy dx is equal to 1/3 times the derivative of x cubed, which is 3x squared, which is equal to x squared, because 1/3 times 3 is 1. So now if I start with this derivative and I want to work backwards to find the antiderivative, it looks like this power is 1 more than this power. And then my function here is being multiplied by 1 over whatever that increased power is. That is kind of the equivalent of the power rule for antiderivatives. If I'm wanting to find the indefinite integral or antiderivative of x raised to some power, we'll call that power n. And then our variable is x. Excuse me. That antiderivative is, well, I'm going to increase the power by 1 instead of decrease. So it's n plus 1. And then it looks like I have to multiply by this constant, 1 over whatever that increased power is. 1 over n plus 1. And then I have to add c on the end, because this is an indefinite integral. Questions on that part? Okay, let's keep going then. Let's say, and again, I'm going to start with a derivative and then work backwards. Let's say if I'm given the function y equals natural log of x or y equals natural log absolute value of x, and I want to find the derivative of those, then dy dx in either case is equal to 1 over x, which I could write as x to the negative 1 if you prefer. Those two terms mean the same thing. Therefore, if I start with this function 1 over x and I want to work backwards and find the antiderivative of that, it looks like I am going to get one of these natural log functions. We're going to assume that I get this function unless otherwise specified. So I'm going to write that down. If I am asked to find the antiderivative of 1 over x with respect to x, or this could be written as x to the negative 1, x to that very specific power of negative 1 instead of any other power here, then that antiderivative is equal to the natural log of the absolute value of x plus that constant c. So that kind of gives us an idea that I need to specify here that this rule works for n not equal to negative 1. Because if it is equal to negative 1, I get a natural log. Questions about that? Okay, so if you can see what we're doing, just like we developed a list of rules for derivatives, I have to develop a related list of rules for finding the backwards version, finding the antiderivative. Let's develop a few more. For some odd reason, your book does not go through these. I have no idea why. At least not in specific form, but I think it's worth going through them. Okay, so if I'm wanting to say, this is my rule, this is my example on the right. If I'm wanting to say, start with the function y is equal to e to the 3x, let's say, and if I find the derivative of that, dy dx, it's equal to, well, I have to use chain rule here to find that derivative. Chain rule tells me that I have to take the derivative of the outside function. Derivative of e to the x is just e to the x, so the derivative of e to something else is e to whatever that something else is. And then I have to multiply by the derivative of whatever is in the power. So the derivative of x is 3, right? If I wanted to modify that slightly and just really didn't want to end up with that constant at the end, then let's say I started with the function y equals maybe 1/3 e to the 3x, which means that my derivative becomes 1/3 times the derivative of e to the 3x, which is e to the 3x times 3, or just e to the 3x. So if I start with this function, e to the 3x, and I want to work backwards and find the function it came from, its antiderivative, it looks like this part is the same, but then I have to multiply by a constant, 1 over whatever this constant is that I'm multiplying by x. So if I'm wanting to list a rule for that, if I want to find the antiderivative of e to the power of some constant times x with respect to x, then that is equal to 1 over whatever that constant is times e to the ax, and then I have to add some constant of integration c. And I'll just make a side note here. If you happen to have the antiderivative of just e to the x with respect to x, then the a value is 1. Therefore, just like the derivative of e to the x is e to the x, the antiderivative of e to the x is just e to the x, plus the c term, of course. Okay, questions on that? Okay, 2 more nice properties of antiderivatives that will be helpful to us that are actually just like your properties for derivatives. Let's see. I'm not going to do the related example, but I'll just tell you a couple of properties. First one, if I want to take the antiderivative of some constant times a function with respect to x. If I'm wanting to take the derivative of a constant times a function, then I take the derivative of the constant part and the function part, and then just multiply it by the constant. I can do the same thing here. This is equal to, I can move that constant out front. Constant times the antiderivative of f of x dx, which will make our differentiation easier, or anti-differentiation, excuse me. And then similarly, just like we can do with derivatives, if I'm wanting to find the antiderivative of some function f of x, and if I'm adding or subtracting another function, g of x dx, then I can split up those two terms. I can write this as the antiderivative of that first function, f of x, and then add or subtract the antiderivative of the second function with respect to x. Those make our antiderivatives a little bit simpler to find. Questions on that? Okay, so we have a list of rules. Let's start using them. Let's find the following indefinite integrals. The following indefinite integrals. integrals. Or you might see this stated as find the antiderivatives. Find the antiderivatives. Two ways of saying the same thing. So the first one, let's do this. Let's find the antiderivative of 10, or excuse me, x raised to the power of 10 with respect to x. I can use the second rule that I developed previously. This is equal to, well, I know I'm going to increase the power by 10 instead, or by 1 instead of decrease. So it's equal to 10, or x to the power of 10 plus 1. And then unlike differentiation, I have to multiply this by the constant 1 over 10 plus 1. Differentiation does include multiplication by a constant, but in this case, we're multiplying by the reciprocal of the power. I have to add my constant of integration, c, to that. I'm going to simplify this. This is equal to 1/11 x to the 11th power plus c. So there's my antiderivative. Questions on that? Okay. Let's find the antiderivative of 3x plus 2dx. And first thing I'm going to do here is I'm going to apply that second property and say, well, this is equal to the antiderivative of 3x dx plus the antiderivative of 2 dx. That's the first thing I see that I can do. Next thing I see is this second term, or this first term has a constant times some function of x. So I'm going to move that constant out front. And this is equal to the antiderivative of 3 times x. And I'm going to write this as x to the 1 power dx plus antiderivative of 2 dx. So now I can apply my rules of antidifferentiation. This is equal to 3 times the derivative of x to the 1. I'm going to use power rule, or the second rule of antidifferentiation. This is 1 over 1 plus 1, which is 2, times x to the 1 plus 1, which is 2, plus c, plus antiderivative of 2, which is a constant. Use that first rule. So this is 2 times x. I'll call this c1 plus c2. Okay. I'll write that down in a simpler form. It would be 3 halves x squared plus c1 plus 2x plus c2. So now I've found the antiderivative. I'm going to rearrange this a little bit. I can add in any order that I want. This is 3 halves x squared plus 2x plus c1 plus c2. Right, these are both constants of integration. Constants of integration. Do you guys have questions about that part? Okay. This might get a little troublesome if I have to add some constant of integration every time I split up a sum of functions into different derivatives. But one thing we might note here is I have no idea what these constants are, but I do know that their sum will also be constant. If I add 2 to 4, then 2 is a constant, 4 is a constant, 2 plus 4 is 6, also a constant. So because I really have no idea what these constants are, I actually don't need to write a separate constant of integration for each little antiderivative that I find when I'm calculating an antiderivative. I can just kind of tack on a plus c at the end. I could just say, instead of plus c1 plus c2, I could just call that whole thing c. So this becomes 3/2 x squared plus 2x plus c. So I can do all of my integration steps, all of my finding my antiderivatives, and then as a very last step in my solving process, I can just add this c on the end. So I don't have to worry about it in the middle of calculating. Okay? So that makes things a little bit easier. Let's do one more. Let's find the antiderivative of this. 3 over x to the 5th plus e to the x minus the 6th root of x. And that whole thing is with respect to x. First thing I'm going to do is I'm going to rewrite this. This is antiderivative of 3 over x to the 5th dx plus antiderivative of e to the x with respect to x minus antiderivative of the 6th root of x with respect to x. Okay. I don't have a rule for antidifferentiation that allows me to take the antiderivative of something divided by something. So I need to somehow rewrite this to where it fits the form of one of the rules that I have. It's kind of an important point. To apply rules of antidifferentiation, to apply the rules of antidifferentiation, the integrand must fit the form of one of the functions I'm given in the rules. The integrand, so that's the thing that I am finding the antiderivative of, it must fit the form of one of the rules that I'm applying, or of the rules given. So I have to write the integrand as, say, x raised to a power, not 3 over x raised to a power, or as e raised to a power, not 1 over e raised to the power, etc. So I have to bring in algebra here. So I'm going to rewrite the following using algebra. Algebra in very similar manners as we have done for derivatives. This is equal to the antiderivative of 3x to the negative 5th dx plus e to the x is already in one of the forms for a rule that I have, so I don't have to rewrite that one, minus the antiderivative of 6th root of x is the same as x to the 1/6 power with respect to x. Okay, Now that I've rewritten those, one thing I can do is this 3, this constant, I can move it out front. So I'll go ahead and do that. Let's put it out here. Okay. And now I can apply my rules of anti-differentiation because I have written all those functions in a form for which I have a rule to apply. This is equal to 3 times the antiderivative of x to the negative 5th, which is x to the negative 5, and then that power is increased by 1, multiplied by the constant 1 over negative 5 plus 1, plus antiderivative of e to the x, which is just e to the x, minus x raised to the power of 1/6 increased by 1, multiplied by 1 over that power of 1/6 also increased by 1. I've applied all those rules. I have to add my constant of integration c to the end. Questions so far about that? Okay, I am going to simplify this. So this is equal to a constant of 3 times 1 over negative 4, x to the negative 4th, plus e to the x, minus 1 over 1/6 plus 1 is 7/6, x to the 7/6 power, plus c. I can do a little bit more. 3 times 1 over negative 4 is negative 3/4 x to the negative 4 power, plus e to the x, minus 1 over 7/6, which is 6/7, x to the 7/6, plus c. One other simplification I might do here actually is rewrite this term with a positive exponent. So let's rewrite it as negative 3 over 4x to the 4th. So there is the antiderivative of my function. And you could actually check yourself on this. Remember, I'm going backwards. I'm finding this is my primitive, or my antiderivative, f of x. And we had a property of that when we started this that said that f prime of x should be equal to little f of x, that function that I began with. So if I want to check myself, I can take the derivative of this function. So let's do that. I can check this. I can differentiate d dx of, I'm going to write it as above, negative 3/4 x to the negative 4th plus e to the x minus 6/7 x to the 7/6 plus c is equal to the derivative of negative 3/4 x to the negative 4th, negative 3/4 times a negative 4 x to the negative 5th power, plus the derivative of e to the x, which is e to the x, minus 6/7 times the derivative of x to the 7/6, which is 7/6 x to the 7/6 minus 1, which is 1/6, plus the derivative of a constant, which is 0. That c term is a constant, which gives me 3x to the negative 5th plus e to the x minus 6/7 times 7/6 is 1. So that would be x to the 1/6, which is exactly what we started with, which is what we would hope to get. Do you guys have any questions on that? Okay then. Well, that is all the time that we have today. I will post more videos on this section for tomorrow. And I think we're done. Unless you guys have burning questions on your mind. Okie dokie. Well, I will be around later on in the morning then, if in my office, if you happen to have questions. Otherwise, I will talk to you guys later. Have a good weekend.